Hello, everyone, and welcome to part one of our two-part microplastics webinar series, co-hosted by Shimadzu Scientific Instruments and our friends at Frontier Labs. My name is Alan Owens, and I will be the moderator and co-host for the two-part webinar series on utilizing PY-GCMS for microplastics analysis. Before we get started, just a couple notes for everyone viewing. There are a few items worth mentioning in the webinar console. Each of these items on the screen can be expanded by clicking and dragging from the bottom right of each window. If you're like me, you might accidentally close a screen and wonder where it went. At the bottom of the console, there is a widget bar that will open any windows you've accidentally closed. In that widget bar, from left to right, first, you'll see a yellow question mark. This is for help if you've experienced technical issues during the webinar. Next, the blue projector screen is the presentation window. The red film strip next to that is the media player. The purple Q&A is our question box. If you have any questions throughout the presentation, go ahead, type your questions in the box, and submit them. At the end of the presentation, we will be answering the questions you submitted during our Q&A session. If your questions are not answered, fear not. All questions will be answered post-webinar. The other blue box are the speaker bios if you want to know more about us. And finally, the green paper is our resources list. We have an information-packed webinar today, and we can't wait to get started. First off, I would like to introduce myself. My name is Alan Owens, and I am the GC and GCMS product manager here at Shimadzu Scientific Instruments. I have been with Shimadzu for 7 years, and specifically in the role of product manager for the previous 2 years. Since the beginning of my tenure with Shimadzu, I have been exposed to the strengths and the expansion of capabilities the Frontier Pyrolyzer provides as a sample introduction technique. It is also my pleasure to co-present this webinar by none other than Rosine Belgame, the Technical Director at Frontier Labs America. She has more than 10 years of experience in pyrolysis as well as multiple other analytical techniques, and we thank her for her support and efforts to make this webinar possible. With that, let's get started. We have a lot of information to share with you during today's webinar. First, we will take a look at the general overview of microplastics. I'm sure most people in attendance of today's webinar are familiar, if not authorities, on the subject matter, but we would like to take the time to discuss exactly what microplastics are. We will also highlight what makes microplastics as a whole innately difficult to characterize, measure, and/or quantify, and why these difficult analytes are alarming in terms of an environmental concern. Following up the overview of microplastics, we will then discuss the different techniques used to analyze microplastics, and with an overall focus on PY-GCMS. And finally, I will then hand it over to Rosine, who will go into more detail on the simple yet efficient solution Frontier provides in tandem with our Shimadzu GCMS for the characterization and quantitation of microplastics. So, what exactly are microplastics? Well, microplastics can be defined as small plastic particles that are roughly less than 5 millimeters in size. Typically, microplastics are the breakdown products from larger single-use plastics that break down over time due to environmental conditions and weathering. Although the effects of microplastics are not completely understood, many countries have placed bans on single-use plastics in an attempt to slow down the contribution of microplastics to certain ecosystems. Larger plastics, such as resin pellets, often used in plastic manufacturing, and even microbeads used in healthcare and beauty products, are not new. In fact, microbeads have been around for some time, but it wasn't until 2015 until microbeads were banned from healthcare products. Even though plastics are not new, the breakdown into microplastics and their effects are a growing concern today. As they continue to weather, the breakdown can continue to even smaller pieces classified as nanoplastics, which are roughly less than 1 micrometer. At this moment in time, plastic waste is the most prominent type of marine debris found in our oceans and lakes, where it represents nearly 40% of the litter found on our beaches. In addition to this, nearly 8 million metric tons of plastic enters our oceans every year. In fact, there are certain reports that suggest the mass of microplastics will actually surpass that of fish in aquatic habitats as early as the year 2050. With this in mind, it is important to understand where all of these plastics come from and the specific points at which we can eliminate further contributing to the problem. Without a comprehensive analytical process, estimates of plastic waste of aquatic ecosystems can vary widely, and even less is known about microplastics contamination of non-aquatic environments such as soil as well as the atmosphere. The plastic life cycle usually begins with production, where raw materials are extracted through either mining or drilling, requiring lots of energy. During the plastic production, these raw materials are subjected to high amounts of heat and pressure, where nurdles, or small plastic nuggets, begin to shape. From production, we head to manufacturing, where products are created using the plastics. And it's at this stage where we can see, via the diagram on the slide, that this is the first point at which plastics can make their way into various ecosystems. From use of those plastics to post-use, many pathways can also form. However, one of the more costly steps in terms of microplastics occurs at landfills, where a single-use plastic bag can take up to 10,000 years to fully decompose. And even then, the plastics will usually degrade into microplastics, which is why we're here. As we continue to learn and understand the life cycle of plastic, one thing is for certain: plastics and microplastics are here to stay. In summary of the environmental concerns microplastics produce, we can see here the sheer amount of plastic pollution the world contributes to our oceans. In terms of plastic waste, there are millions of tons of waste that are accounted for globally. Even though this 2019 study reports a fraction of that mass actually being microplastics, this number will surely grow as more and more plastics are degraded or broken down into microplastics. With the large amount of plastic waste continuing to grow and show signs of health concerns, not only to aquatic life, but now also to humans, the need for an analytical method to characterize and quantify those microplastics has never been more important. Now that we've talked about what microplastics are, where they come from, and what makes them so tricky to get rid of, let's talk about what makes the characterization of microplastics so difficult. So what makes characterization of microplastics so extremely difficult is the varying chemical makeup and combination of multiple products present. As we can see here on the slide, listed are just some of the more prominent polymers representative of plastic composition. These polymers are also comprised of additives ranging from plasticizers to colorants to stabilizers. The list of products is even more vast when we consider what the plastics are used in, such as primary products to secondary products, much like that of insulation, clothing, and pipes. What's unique about these plastics is the diversity of morphology or shape in which they can take. As more knowledge of microplastics is uncovered, we begin to see what microplastics have the ability to bind to certain ecotoxins, like PAHs, PCBs, heavy metals, and much more, which makes the need to not only characterize them, but quantify them imperative to certain health and environmental concerns. So, the most important question here is, how do we determine the concentration, the size, and the identity of these microplastics? There are various analytical techniques that have been used and newly implemented in the attempt to answer the question from our previous slide. In terms of microplastics, techniques such as FTIR, FTIR with imaging, elemental X-ray, MALDI, and of course Pyrolysis-GC can be utilized for characterization and quantitation of microplastics. For trace and sorbed components, like those mentioned in the previous slide, such as PAHs, PCBs, etc., Pyrolysis-GC can also be used for this analysis, along with the techniques like LCMS, liquid injection GCMS, and EDX. In our expedition to find an analytical technique to perform well in all areas of characterization, it is important to understand that there is not one technique to solve the puzzle, but a combination of techniques that complement each other for microplastic analysis. Of course, in this webinar, we are going to shift our focus towards Pyrolysis-GC, one of the most comprehensive analytical methods in characterizing and quantifying microplastics. Each technique has its pros and cons, but we wanted to differentiate between two of the most common while highlighting PYGCMS as the most thorough technique. When compared to common spectroscopic solutions, Pyrolysis-GC excels in some pretty important areas. One of the major advantages of PYGCMS, even though it is a destructive technique, is the fact that it is designed for polymer composition and has the ability to classify specific additives that might be present. While PYGCMS cannot exactly determine particle size and shape, it is not limited in the size or amount of particles that need to be collected for analysis. With this advantage, PYGCMS, or Pyrolysis-GC, can stretch the LOD lower than before and remove any bias on accurate concentration at lower levels. If you return for part 2, we will dive into this a little bit more. In addition to the more accurate concentration at lower levels, the morphology of microplastics leads to complications using spectroscopy due to the smaller size, shape, and color of some potentially translucent polymers or additives. And finally, microplastics sampled from various ecosystems have almost always been subjected to some form of weathering. Weathering changes the composition of pure polymers, making them possibly difficult to identify. But with Pyrolysis-GC, this uses the chemical backbone of the polymers and additives for identification, making it extremely accurate for real-world samples. With all of these benefits and more, PYGCMS may just be the solution you need to either jumpstart or strengthen your workflow for microplastics analysis. In summary, Pyrolysis-GC is a robust yet simple technique for analyzing microplastics. With very limited sample prep, full composition analysis of microplastics is possible. PYGCMS also negates the potential obstructions of adverse matrix effect and does not exclude polymers based on their size or their shape. Another major benefit of PYGCMS would also be the mass concentration reported, which is always reported in conventional units such as micrograms per liter, whereas the mass concentration typically is inferred using spectroscopy techniques. Another added benefit of the Frontier Pyrolysis unit is that its furnace directly integrates with Shimadzu's GCMS inlet, removing any sample loss and provides excellent quantitative repeatability. With the most sensitive GCMS on the market here at Shimadzu, paired with Frontier's pyrolyzer and autosampler, you can utilize a complete solution for microplastics analysis. And for more on that complete solution of microplastics analysis, I would like to turn it back over to Rojin, who will share all of the insight as to what makes PYGCMS such a powerful technique, as well as their complete microplastic solutions from Frontier.
Thank you very much, Alan, for the introduction and the background. So now let's talk about the Pyrolysis-GC technique and its capabilities for microplastics analysis. We will go over the microfurnace Pyrolysis-GC system configuration for microplastic and its workflow. We then look at the main components of the configuration to really better understand how the microfurnace pyrolyzer is used to quantify and identify the microplastics. The main components we will focus on today are the microfurnace pyrolyzer, the FSERT software that is used for analyzing the microplastics, the standard calibration kit, and the column kit that are designed specifically for microplastic analysis, and our speedless sampler that enables you to perform a speedless analysis. Although microfurnace pyrolysis GCMS has a very broad application in polymers and additives, we focus on microplastic analysis in today's event. We will briefly go over the capabilities of the microfurnace, but we also have many other available resources for you that go into much detail about this technology and its application. So what is pyrolysis GCMS technique? By definition, pyrolysis is a thermochemical decomposition of organic compounds at elevated temperatures without the participation of oxygen. It involves simultaneous chemical composition and physical phase change and is irreversible. Flash pyrolysis is used to generate pyrolysate, which evolve into the GC column for analyzing microplastic polymers. Mass spectrometer, or the MS, then detects the pyrolysate and produces a pyrogram. Polymer contents are then identified and quantified using MS interpretation libraries. Here is the comprehensive system configuration using your microfurnace pyrolysis GCMS for microplastics analysis. Some of the components are application dependent. For example, the microjet cryo trap is an accessory that is used if you want to analyze any light additives or use the splitless analysis. The microfurnace pyrolyzer directly connects to your GC injection port. So your pyrolysis will be a continuous analysis where all the pyrolysates are deposited directly and continuously on your GC column as they are generated. You can also use the AutoShot sampler shown here as number 2 to automate up to 48 analysis. Specific to microplastics analysis, we also developed a column kit, a packed GC glass liner, the Microplastics Calibration Standard Kit, and F-Surge MP software. The multifunctional splitless sampler and microjet cryo trap are other accessories that you can use based on your application of interest. The workflow is very simple and easy using your microfurnace pyrolysis GCMS. Step 1 is sampling. You simply place a few micrograms of your sample or the calibration standard sample into an inert sample cup. Step 2 is to place the sample cup into the AutoShot sampler and start the analysis. And step 3 is the data interpretation using your F-Surge MP software. So now let's look at the microfurnace technology, how it functions, and what sets it apart from the other pyrolyzers in the market. As I mentioned, the low-mass ceramic microfurnace pyrolyzer directly connects to your GC injection port. So there won't be any transfer line or any dead volume. Sample introduction is also nearly instantaneous. The sample is placed in an inert sample cup and is held at near ambient temperature in helium with no exposure to heat before the analysis. The microfurnace is then preheated to the desired temperature that is precisely measured with a thermocouple sensor. The sample cup then drops into the quartz pyrolysis tube where the sample is rapidly and reproducibly pyrolyzed. The pyrolysates are then directly swept onto the GC column for separation and detection by your MS. Low and high molecular weight and polar compounds can be detected and analyzed by directly depositing all pyrolysates on column in a single step for a continuous mode analysis. The microfurnace also guarantees reproducibility and accuracy of the temperature within plus or minus 0.1 degrees Celsius. The microfurnace is a multifunctional furnace. That means that you can perform multiple analytical techniques such as evolved gas analysis, thermal desorption, hard cutting, and flash pyrolysis. So the microfurnace can perform both thermal and separation analysis with isothermal or temperature program settings. Evolved gas analysis, also known as EGA, is the thermal analysis of your sample that shows your sample's thermal behavior toward the temperature by temperature program heating of the sample and directly detecting the evolved gases with MS. The other modes of operation, such as the flash pyrolysis, or we also call it single shot, the double shot, or hard cutting, are the separation analysis, where you would use a separation column to characterize the organic composition of your sample. For microplastic analysis, we typically use the flash pyrolysis, or the single shot mode of operation of the microfurnace, which is a continuous pyrolysis, as we learned, of your sample using the separation column. The other modes of operation can also be used with the same system based on your application of interest. Now let's talk about FSearch-MP's software. FSearch-MP is an analytical software used with the data obtained by Pyrolysis-GC for microplastics analysis. It allows you to easily and accurately identify and quantify unknown microplastics in the environment. It consists of a patented search program with mass spectral libraries of pyrolysates. The software also automatically creates calibration curves for the registered polymers based on the analytical results from the reference polymer mixture. There is a library for 12 commonly used polymers, as shown here, and you can also create your own libraries for any additional polymers. There are 4 straightforward steps for the operational process by FSearch-MP. Step 1 is to create a plot of the retention index. The retention index is actually created based on the pyrolysates of microplastics calibration standards. Step 2 is creating the calibration file based on the pyrograms of microplastic calibration standards. Step 3 is searching for results of microplastics that are both quantitative and qualitative. And step 4 is reviewing and the confirmation of searching results. So now let's go over each step. So here you can see step 1 in the FSearch-MP software, in which the retention index is automatically adjusted based on the pyrolysates of polystyrene using the microplastic calibration standard. You can perform this step by simply clicking on the RI-cal from STD sample in the software, which is the retention index calculation from the standard sample. Then FSearch-MP software creates the calibration curves for each 12 polymers with extracted ion chromatogram peak of preset quantitative ion. In just a few seconds, you can then see the quantitative and qualitative results, the MS spectrum, and the peak shape for each polymer. Here is a closer view of the search result. You will get the match quality percentage for each polymer, the quantitative result in micrograms, the relative amount in percentage, and the peak area. Also, a bar graph of each polymer's relative percentage amount will be at the bottom of your search result. As you know, with each interpretation library and software, the results must be reviewed and confirmed. So at your last step, you want to check for the peak shape, retention time, mass spectrum, and peak integration area of each polymer listed in your search result. The Microplastics Calibration Standard Kit allows you to create calibration curves to quantify microplastics easily. 2 microplastic calibration standards with different diluents, SiO2 or CaCO3, are available. Both samples contain a few micrograms of each commonly used 12 polymers, which are homogeneously dispersed with a solid diluent for easy weighting on semi-microbalances. Since the quantification target is microgram order or below, ultra microbalance is needed to measure sample weight in a microgram range or less. However, we also developed a sampling method for those with only a semi-microbalance in the lab to measure microgram order samples. You add SiO2 or CaCO3 diluent into your environmental sample. For example, you add CaCO3 diluents 100 times larger than the environmental sample and then dilute the environmental sample. If you measure 1 milligram of the diluted environmental sample, it means that you measure 0.01 milligram of the environmental sample. So this sample prep enables measuring a small amount of sample using a semi-microbalance. We also recently released another microplastic calibration standard kit for quantitative analysis of trace microplastic samples. With this kit, both standards also contain a few micrograms of the commonly used 12 polymers, which are homogeneously dispersed with a solid diluent for easy weighting on semi-microbalances. However, this new product has a polymer concentration of approximately 1/10 of the regular MP calibration standard set. For sample preparation, you need to prepare calibration standards and your environmental sample. We provide the microplastic calibration standards of 12 polymer mixtures to you. So you just need to measure the weight of your calibration standards to create the calibration curve. You might also need to do some pre-sample treatment for environmental samples to remove proteins, organics, and inorganic. Then if needed, you can use our cryogenic meal device to homogenize the sample, then pyrolyze about 0.1 milligram of your unannounced sample. This table guides you how to select the appropriate microplastic calibration standard. You can select the type of microplastic calibration standard based on your target polymers. So if you don't have any target at first, you can start with MP's CaCO3 standard that can pretty much target all of the 12 polymers, but with low sensitivity to PET. In that case, for targeting PET and or PC, you can use MP's SiO2 with TMAH, tetramethyl ammonium hydroxide, which is an alkali reagent used for reactive pyrolysis to improve the sensitivity. Also, as shown here, with MP's SiO2, PU cannot be targeted because its quantitation peaks react with PET and nylon 6,6 pyrolysate. So in that case, if you are targeting PU, you would need to use the MP's CaCO3 standard sample. The UAMP column kit consists of the separation column, a pre-column with a medium polarity, and a UA connector. This product improves the accuracy of qualitative and quantitative analysis of plastic mixture using Upsurge MP software. Also, it reduces the contamination of the separation column, thus reducing the replacement frequency. Here we are showing one example of how the UA pre-column improves the separation and identification of C8 pyrolysate generated from PE from cyclophenodiene, which is a pyrolysate of nylon 6,6. With the UA pre-column, as you can see here, the co-eluding pyrolysates of PE and nylon 6,6 can be separated and identified. We also have a packed GC glass insert to improve the peak shape of pyrolysates generated from microplastics. In addition to a better peak shape, the packed GC glass insert also increases the accuracy of qualitative and quantitative work of a specific plastic in polymer mixture samples. The top PE pyrogram that is shown here was obtained using a regular GC glass insert without any packing. And as you can see, from C20 to C30, the peaks are very broad and have lower peak heights. Now, the bottom PE pyrogram was obtained with a packed GC glass insert. And as you can see here, the peaks are sharper and peak heights are improved. So the last accessory we're going to talk about today is the multifunctional splitless sampler that allows you to perform the new splitless pyrolysis, backflush, solvent cut, and also improve the peak separation. So in a normal splitless pyrolysis, the low helium flow rate can cause secondary reactions that are greatly changed the pyrogram profile. With the new splitless pyrolysis using the multifunctional splitless sampler, A higher helium flow rate reduces those secondary reactions and increases sensitivity by about 50 times compared to the split of 1 to 50 pyrolysis. Higher boiling point compounds in pyrolysate tend to remain in a separation column, resulting in ghost peaks. So the multifunctional speedless sampler prevents contamination of the separation column by backflushing the high boiling compounds in the pre-column, thus significantly shortening the analysis time. And you can also perform solvent cut to win the solvent and protect your system. So with that, this is all I had for today. Now I would like to return the mic back to Alan.
Thanks, Regine. Once again, we appreciate your efforts and teamwork in making this such a success. And a big thank you to all of you who have joined us to learn more about microplastics analysis, as well as the Shimadzu Frontier solution for microplastics analysis. Please be sure to join us next month on Thursday, July 20th at 3 p.m. Eastern for part 2 of our microplastics analysis, where we will hear from Andy Sandy, Shimadzu's application scientist, on his method validation of PYGCMS using the Frontier MP kit and methodology. We will also hear from Athena Nguyen, tech support specialist from Frontier Labs America, to discuss her microplastics analysis of air samples. We appreciate everyone's attendance and hope to see you next month for part 2. With this being the conclusion of part 1, we would now like to open it up for Q&A with questions from our chat. As a reminder, if we do not get to your question, we will follow up via email to answer your questions directly. We thank you again so much for your time, and we hope to see you again in July.
So it seems that we have a few questions in the chat. So we're just going to go through these and answer as much as we can. If we run out of time, as I said in the presentation, we will follow up on everyone's individual questions via email after the presentation. As a reminder as well, this entire session has been recorded. You will be sent the recording either via email, or you can access the recording from the registration link. Slides, as well as the additional resources that were found at the bottom of the presentation window, are also available for download. So for those of you who are asking for recordings, these will all be provided to everyone in attendance, and for those of you who could not attend, they will also be provided to you. So for the first question, we have regarding compatibility of past instruments. So in our presentation, I believe I focused on specifically the 2020 NX, our newest single quad. However, I'm sure there are plenty of customers out there with older instrumentation. And the answer to compatibility would be yes. So the pyrolyzer, as well as the auto shot and the additional accessories, including the MP kit, all of these are backwards compatible with our older GCMS units. I think the best thing that you could possibly do would be to reach out to your sales engineer or even your tech support engineer. One of the things that we would like to confirm more than likely is your computer operating software, to make sure that there's not going to be any miscommunication, that we get you the right control software for the pyrolysis and auto shot. But for the most part, all of the things that were mentioned in today's presentation on Rogine's side are compatible with previous Shimadzu instrumentation. So there shouldn't be any issues there whatsoever. The next question we have here is in regards to carrier gas. So with the helium shortage continuing to be an issue, can the PY, or the pyrolysis unit, work with alternative carrier gases? The answer is yes, and I would like to make this a two-part question. All of Shimadzu's GCMS units, especially the current GCMS NX units, are all compatible with multiple different carrier gases, including hydrogen and nitrogen. So out of the box, the instrumentation, the hardware, the GCMS itself is compatible with alternative carrier gases. We have several guides established that can be found by either accessing the Shimadzu website or contacting your local sales engineer. And we have starting guides or getting started guides for hydrogen or even nitrogen analysis. In terms of the PY side of things, the answer is also yes. We do have some applications in the work currently where we're actually doing some MP kit studies via the solution that Rogine touched on today with alternative carrier gas, specifically nitrogen. We hope to have the results for the alternative carrier gas published later this year, but we'll be sure to get that out as soon as we possibly can. So in terms of compatibility with alternative carrier gases, the absolute answer is yes, and we are currently working on getting some application data out very soon. So the next question that I see here is, I believe this one's going to be for Rogine actually. Does FSearch MPs 2.1 contain library information for other polymers or additives? Rogine, would you like to take that one?
Sure, Alan. So yes, the answer is FSearch 2.1, although it is specifically designed for microplastic analysis, which means you have a quantification part of the software which can quantify the polymers, but it also comes with some qualification libraries that are Pyrolysis-MS and the Additive-MS, where it allows you to identify other polymers as well. And if there is any polymer that is not listed there, or if you want to perform quantification work other than 12 polymers that are inside FSearch MP 2.1, you could always add it to your library and use like an in-house or a user library. Also, we didn't talk today, but we do have another FSearch package that is called FSearch 3.7, and that's more of a comprehensive library software where you have 4 unique libraries, EGA-MS, Additive-MS, the Pyrolysis-MS, and the Polymer-MS. So not only it has, of course, thousands of polymer because that one is comprehensive toward polymer and additive analysis, but not only it gives you peak-by-peak identification, it also tells you where that pyrolysate is coming from, so the source of origin of the polymer. And also, it gives you the integration summation of a pyrogram. So when you run a sample, instead of doing individual peak-by-peak analysis to identify or qualify your polymer, you could actually perform an integration summation of the whole pyrogram. And the library will find a match for the polymer for that specific pyrogram. So there are some overlays between 2.1 and 3.7, but the 2.1 is specifically for microplastic, for quantification and qualification of some polymers.
Wonderful. Thank you, Rogine. Moving on to the next question, we have, are there the ultra-alloy microplastic column kits with different dimensions depending on the application goal or carrier gas, etc.? And the answer is yes. I'll take this one. The answer is yes. So Frontier provides or offers a wide range of the ultra-alloy columns and a few different dimensions specifically for the MP kits as well. Anything and everything that you've seen today regarding the MP calibration standard set, the FSearch, vials, consumables, anything that you might need for the pyrolysis unit, FSearch is sold directly through Shimadzu. So we partner with Frontier, and everything that you might need for this analysis or any other pyrolysis analysis, Shimadzu has part numbers and pricing for. So we can provide the total solution for you guys from GCMS all the way through pyrolysis at one place. So if you're looking for the calibration standards, if you're looking for column kits, the libraries, regardless of the dimensions, we have all of Frontier's catalog within Shimadzu's part number system, and we would be more than happy to provide any consumables or standards that you might need. Okay. I see another question in the chat. Rogine, I think this is for you. And the question is, where can we get the FSearch software from? Is there a link for it? I think maybe you would like to touch on your availability to do demos and things like that.
Sure. So yes, of course, we can do a live demo. Alan and myself, we can perform any demo on 3.7 or 2.1. As Alan mentioned, in terms of purchasing it and having it for your own licenses, which comes with 3 licenses for the S-Search MP 2.1, that will be through Shimatsu. So you would just purchase those software from Shimatsu. For the 3.7, that's the same. Shimatsu sells it. For 3.7, we do have a 30-day trial on our website, which is a limited version of it, but that just kind of gives you a feel and understanding of how the F-Search works. The 2.1, there is no trial as of right now, and all the purchases can go through Shimatsu.
Wonderful. Thank you, Rojin. Okay, I think we have time for a few more questions. I have one that I believe is kind of a good follow-up for something that I briefly discussed in the presentation earlier. Can both microplastics and sorbed components be analyzed on the same instrument? And I'll take this one away. In terms of doing microplastics analysis as well as the sorbed components, remember those sorbed components are going to be your PAHs, PCBs, some of those ecotoxins. We do actually currently have an application note on our triple quad doing some of the ecotoxins that might potentially cause concern, that could potentially sorb onto certain microplastic polymers. That is currently up on our website, and we can provide that as well. But that's a really good application that shows just the fact that our Shimadzu system, along with PY, can do everything in terms of microplastics analysis, as well as some of the sorbed component analysis via triple quad. So we do have an application on that, and if you're interested in receiving that application note, we can absolutely provide that, and it is on our website as well. And I believe we have one more question here that we can answer. Rojin, I'm going to pass this one off to you. Can the double shot mode of operation of the microfurnace be used for microplastic analysis?
So yes, as we discussed, there are multiple modes of operation that you'll be able to use the microfurnace. Typically, flash pyrolysis, which is an isothermal, most often is at 600 C, that is used for polymer analysis in microplastic. Although if you have to do reactive pyrolysis, which is then adding your TMMH to it, alkali reagent, that's typically done at 400 C, but that's an isothermal flash pyrolysis. Now, we do also have customers who are using a double shot or even the hard cutting mode of operation for microplastic type analysis, and that's the cases where you want to thermally extract the additives or any lighter compounds or volatiles from your sample first, and then obtain a pyrogram for your sample. So with the double shot, the way with microfurnace it works is the furnace is heated to the desired temperature. Say, for example, you run your EGA, you obtain a hump or peak from 100 to 250, for example, and that gives you the optimal temperature zone that you want to set your furnace to perform thermal extraction of your sample. So once your furnace is set at 100, the cup free falls into your furnace. 100 to 250, for example, then cups go back up again while the GCMS is performing and obtaining the thermal desorption chromatogram. And then at that point, the additives are thermally extracted from your sample. The second shot on the same sample, for example, 600 C, then once the furnace is preheated to 600 C, the cup again free falls into the furnace, where now you're performing flash pyrolysis on it, and then you obtain a pyrogram for more polymeric and heavier component of your sample. So typically, you would use flash pyrolysis or single shot for microplastics and polymer analysis, but if, again, there are cases where you want, for any reason, extract additives or any unwanted other compounds or area of your sample that you know you want to thermally extract it, you could use the double shot or the hard cutting.
Thank you so much, Rojin. I appreciate your answer. I appreciate your time helping us out with this webinar today. I just wanted to follow up again with thanking everyone for their time and attendance here. I apologize if we did not get into any of the specific questions that you might have entered into the chat, but as I mentioned before, we will reach out directly via email to set up some time to communicate and hopefully answer all the questions that you may have. As a reminder, don't forget, we will be having our second part of the Microplastics webinar series coming up in July. That would be July 20th at 3 p.m. Eastern Time. We have a really fun webinar set up on part 2, where we have Andy Sandy, our Shimadzu application scientist here, who's going to be talking about his method validation of the MP kit. And then we also have Athena from Frontier Labs, who will be covering her application on some microplastic sampling in air. So we really hope to see you guys again. And in the meantime, if you have any follow-up questions or any requests for downloads, don't hesitate to reach out. We will be sure to provide everything that we possibly can. And we will talk to you all soon. Thanks so much, and have a great rest of your day. Goodbye.